Hello, dear colleagues. We will continue today the chain of our scientific seminars devoted to relationship between philosophy and mathematics. And we are glad to present our reporter, our speaker, Dr. Pravina Agarwala, Department of Mathematics, Anand International College of Engineering, India. And so, dear Dr. Pravina, please, you are welcome. You have 20 minutes.
Yeah, thank you very much, Professor Ruzana, and thank you very much all the colleagues from the People's Federation University of Russia. So welcome this talk, and I'm thankful to all the organizers. The title of my talk is the Fractional Hypergeometric Functions and Applications. The aim of this is the outline, aim of the talk, introduction, classical beta and gamma function, extended hypergeometry function, introduction to fractional calculus, fractional differential and integral operators, fractional integral formulas, conclusion, future perspective, and references. So the fractional calculus of hypergeometry functions has a significant importance and application in various fields of science and engineering. Here we aim to discuss study of extensions and generalization of hypergeometric functions. Then we little bit discuss about the introduction of fractional calculus, which is a part of the new calculus. And then we discuss about the fractional integral and differential formula of the extended hypergeometric type function by using the one of the very well-known fractional operator, Marchi-Saigo-Maeda operators. So, colleagues, in recent years, many extensions and generalization of spatial functions witness a significant evolution. This modification in the theory of spatial functions offers as an analytical foundation base for many problems in mathematical physics and engineering sciences, which have been solved absolutely and which have various practical applications. The theory of spatial function revolves around the two most important basic spatial functions, that is called the beta function and gamma functions, because most of the spatial functions are expressed either in terms of the beta function or gamma function. So this is the definition of the classical Euler's beta function, which is given by the equation number 1, and the gamma function, which is given by the equation number 2. So the study of the extensions of the spatial functions began in early 1990, and Chaudhary and Jubair, they extended the gamma functions in 1994 first time and studied some basic properties as defined in the following equation number 3, which is represent the extended gamma functions, and in equation 4, which is represented by the Chaudhary et al, is a extended beta function. Then, in continuation, the another research group from the Turkey, they have used the convoluent hypergeometry function to generalize the classical beta and gamma function, which is given by the equation number 5. You can see that at here, which is represented by the equation. This is the Euler's gamma function, and which is given by the equation number 5. And the classical beta function, which is given by the equation number 6. Then, after that part, they have developed. Yep, what happened? What happened? Okay. Then, inspiring the above work, very recently, Goel et al. have introduced an extension of the beta function using the Riemann function, have studied various properties of these extended beta function, which is given by the, we can say that, we can represent by the equation number 7. So it is a basically 2-dimension of the gamma function. Not 2-dimension, we can say that it's a 2-parametric beta function. Okay, then the definition of the extended beta function, which is given by the equation number 8. Here you can see that the condition of the extended beta function, which is given by the minimum real part of x1, x2 is greater than 0, and real part of r1 is greater than 0, real part of r2 is greater than 0, and the E of R1, R2 is the 2-parametric Metcalfe function, which is called the Riemann's function. In the above extension, Goel et al. Have used 2-parametric Metcalfe function as a kernel to modify the classical Euler's beta function in terms of integrals. Then, in 2011, Orjanin et al. Have used the convolutional hypergeometric function to generalize the classical Euler's beta function, which is given by the equation number 5, 6. I have already mentioned it this part. Now we are going to the next slide, I think. Sorry, it is a, yeah. Then, if we set R1 equal to 1 and R2 equal to 1 and R equal to 0 in equation n, then we obtain the beta function, which is given by the equation number 1. After that, we developed one of the very interesting theorem to understand the properties of the new generalized extended beta function. So our first theorem, which is given the symmetric relations, you can see that the let R is greater than equal to 0, minimum real part of x1, x2 is greater than 0, and real part of r1 is greater than 0, and real part of r2 is greater than 0. Then the extended beta function defined by 8 satisfy the symmetric relation B of R, R1, R2, X1, X2 equal to B of R, R1, R2, X2, X1. On the same way, we have developed another very beautiful property that is called the functional relation. So you can see that in the equation number 11, they can show that the functional relations, and in which they mention that the B of R, R1, R2, X1, X2 equal to B of R, R1, R2, X1, X2 plus 1 plus B of R, R1, R2, X1 plus 1, X2. So this is the functional relation which is satisfied and true for the extended beta function. Then this another interesting theorem, which is giving the Malin transform of an extended beta function, which is giving by the equation number 12. So you can see that at here we have developed one of the interesting result involving the Malin transform. So 0 to infinity R of s minus 1 B of R, R1, R2 dr becomes B of x1 plus s and x2 plus s, gamma of r1, r2, 0. So this is the Malin transform. Motivated by the above work, Jain et al. Have extended Gauss hypergeometry function, convolutional hypergeometry function, by using above extended beta function and studied various properties of these extended functions. They also studied the increasing or decreasing nature, that is called the monotonicity, long convexity, long concavity of the extended beta function. Then series representation and integral representation of Gauss hypergeometry function to F1, which is given by the equation number 13. And the series representation of the convolutional hypergeometry function, which is given by the equation number 14. Then they have developed some new extended Gauss hypergeometry function, which is represented by the f of r, r1, r2. Okay, and it is defined by the equation number 15, in which we can easily understand f of r, r1, r2, it is equal to the summation n equal to 0 to infinity b of r, r1, r2. It is an extended beta function upon b of p1, p2 minus 1. It is a classical beta function p naught n z raised to power n upon factorial n. If we set R1, R2 equal to 1 and R equal to 0, then we get the Gauss hypergeometry function given by the equation number 13. So on the same way, a new extended confluent hypergeometry function phi of R, R1, R2 is defined by the equation number 17. So, and the convergence conditions are given below, so we can easily find out the generalized extended confluent hypergeometry function. If we set R1, R2 equal to 1, R equal to 0, then we get the Gauss hypergeometry function and confluent hypergeometry function given by 14. Then following functional relations holds for the new extended confluent hypergeometry function and Gauss hypergeometry function. You can see the first relation, which is given by the equation number 19. It is a functional relation for the new extended Gauss hypergeometry function, and the relation 20, which is given the new relation for the extended confluent hypergeometry function. I'm sorry. Yeah. So the following some relation is also holds true for both the extended beta, extended Gauss and extended confluent hypergeometry function, which is given by the equation number 21 and 22. Then for the extended Gauss hypergeometry function, the following result holds true. You can see that this is an interesting result in which the right hand side is having the summation formula between the confluent between the Gauss extended Gauss hypergeometry function and the classical beta function. On the same way, we can develop the one of the interesting theorem for the extended confluent hypergeometry function, and which is holds true, and it is a summation of the two classical extended beta function and the extended confluent hypergeometry function. So the introduction of the fractional calculus is a very important development in the field of the calculus due to the fact that it has been widely applicable in many fields of mathematical, physics, and applied science. The fractional calculus operators having various spatial functions have been used for the modeling of system in turbulence and fluid dynamics, stochastic dynamic system, thermonuclear fusion, image processing, nonlinear biological system, and in quantum mechanics. So these are the pioneers. Those are giving some contribution in the development of the fractional calculus. One of the name is the G.W. Leibniz in 1695 to 1697. Then L. Eulers is giving the very important contribution, but due to the time limit, I am not giving the more information. One of the contributors is the J.B.J. Fourier, then J. Livoli, then Riemann in 1826 to 1866. On the parallel way, since that time, the fractional calculus has drawn the attention of many famous mathematicians such as Eulers, Laplace, Fourier, Abel, Livoli, Riemann, and Laurent. But it was not until 1884 that the theory of generalized operator achieved a level in its development suitable as a point of departure for modern mathematics. By then, the theory had been extended to include operator d nu, where nu could be rational or irrational, positive or negative, real or complex. Thus, the name fractional calculus become somewhat of a misnomer. A better description might be differentiation and integration to be an arbitrary order. Then between the last century, it is practically impossible to name all made important contribution in construction of the early stage of the building of fractional calculus. New era in the development of this branch since began 40 to 50 years ago due to numerous applications of fractional type model is continued up to now. One can mention a large list of area of application as follows. So here I mentioned some of the brief application. Fractional operators appear at study various problem of analysis of differential equation. There is a very important contribution by D.K. Ditlin. Then Kilba Srivastava Truzolia giving the very important monograph. Then Virginia Kryakova, she is developing a many good paper in this direction. Then Miller and Rose, Oldham and Spener book is very popular. Then after that, Pudrobi in a fractional differential equation. It is also very, very important book in this direction. Then Sameko, Kilbas and Machiu, and he is also developing a very good book. Then Marchido, Kryakova, Menardi did develop a very good book in this direction. Then Hilfer is developing another monograph on the application of fractional calculus. Then in modeling and control, there is another book is developed by the World Scientific in Singapore in 2010. Then nano and cosmic physics is by the V.B. Uchken. He is developing a two volumes, 1 and 2 in 2013. So there are a lot of development is happening in this direction. Then after that, we are discussing about some of the definitions. You can see that this is the Riemann-Livoli fractional integral operator, which is given by the equation number 25 and 26. And the Kober fractional integral operator, which is given by the equation number 27 and 28. Then Sameko is introducing the another kind of generalization of the fractional integral operator, which is given by the equation number 29 and 30. After that, the Saigo Maeda is giving the very interesting generalization of the operator, which is given by the 31 equation. It is we call this generalized Saigo Maeda fractional integral operator. And this is the another fractional integral operator. So they are giving the left-hand side and right-hand side generalized Saigo Maeda fractional integral operators. Then we have developed a very interesting definition in which we have using the generalized extended Saigo Maeda fractional integral operator and the generalized Gauss hypergeometry function as a composition formula. We got the result in the terms of the product of the gamma function and the product of the two family member of the spatial functions in the product. So this is the generalization result we got the with the help of the Saigo Maeda fractional integral operator. We call the composition formula, or sometimes we call the image formulas. So by inspiring the above work very recently, I'm sorry. On the same way, they have developed the another result. So we conclude our investigation by remarking that the results presented here are the survey of the fractional hypergeometry functions. We also presented some new results for the Marchev-Saigo Maeda fractional integral operators involving extended hypergeometry functions. Our results have been expressed as the Hedmond product of the extended hypergeometry functions and the generalized hypergeometry function. Some special cases of our main results are easily converted by using the interesting known extensions of the beta function and the other spatial function. In our opinion, during a period of 325 years of fractional calculus, a critical mass of information has been collected from both mathematical and applied viewpoint. And nowadays, it is a suitable moment to make a useful transition. Despite the fact that the use of hypergeometry function for fractional differential equation has reported significant contribution by various researchers, Still, they did not reach the required level to decide always which fractional calculus model is more suitable for given real data. So we think that one of the key to the success of the future theoretical and applied viewpoint is to consider the notation of distinct class of fractional calculus operator, showing exactly both the advantage and limitation of certain type of fractional operators will make this field much stronger in the long range. Harmonizing the point of view that any fractional operator should have a physical, biological, or economical meaning and should appear naturally in a set of real-world process versus to the pure mathematical construction of fractional operators. Without looking to any experimental data, it seems to be a challenging problem for researchers in the area of the fractional calculus. So this work and study were prepared within the framework of the agreement between the Ministry of Science and Higher Education of Russia, number 07515202160, development of the new methodology and intellectual base for the new generation research of India philosophy in correlation of the main word philosophy tradition. This work has been supported also by the RUDN University Strategic Academic Leadership Program. And thank you very much. And these are my some references which I have used during the preparation or study of this work. These are my references. So thank you. Thank you very much.
Thank you very much, Pravin.